lucrativos, carrego uma missão ambiciosa desde o meu nascimento: promover a engenharia em benefício da qualidade de vida da sociedade. Este comprometimento com o desenvolvimento do país me fez começar a utilizar o meu espaço para gerar encontros e conectar pessoas. Como fiz isso? Abri minhas portas para reuniões no âmbito das divisões técnicas, reunindo associados voluntários das mais diversas áreas, a fim de realizar debates, estudos, seminários, cursos e palestras. E posso dizer que tudo isso transcorreu com sucesso. Criei um verdadeiro exército de engenheiros cidadãos que deram vida a projetos que defendem o interesse público, a engenharia e o desenvolvimento científico do país. Projetos que promovem o avanço econômico, cultural e social com ética profissional e determinação. Você pode não saber meu nome, mas com certeza conhece muitos dos meus feitos. Afinal, são mais de 100 anos de história que acumulam experiência, tradição e credibilidade em minha bagagem. Mas não se preocupe, minha missão de contribuir com o desenvolvimento da sociedade não envelhece, ela se renova constantemente. Atuo de maneira integrada, conectada e sem fronteiras geográficas. Meus eventos e reuniões podem ser acompanhados presencialmente ou pela internet. Mantenho meus associados atualizados por informativos e publicações colaborativas, que são escritas pelo verdadeiro protagonista desta história, você. Você pode não ter me visto nascer, mas saiba que contribuiu para que eu estivesse aqui hoje. Afinal, sou feito por pessoas. Se já me conhece, é associado ou contribui com a minha causa, o meu mais sincero obrigado. Se não me conhece, tenha certeza, minhas portas estão abertas para novos associados que tenham o desejo de escrever novas páginas desta história. Apesar de ter nascido no passado, sempre atuarei por um bom futuro. Muito prazer, somos o Instituto de Engenharia. 1916. Quando minha história começou, você ainda não havia nascido, mas eu já pensava em você. Apesar de não ter fins lucrativos, carrego uma missão ambiciosa desde o meu nascimento: promover a engenharia em benefício da qualidade de vida da sociedade. Este comprometimento com o desenvolvimento do país me fez começar a utilizar o meu espaço para gerar encontros e conectar pessoas. Como fiz isso? Abri minhas portas para reuniões no âmbito das divisões técnicas, reunindo associados voluntários das mais diversas áreas, a fim de realizar debates, estudos, seminários, cursos e palestras. E posso dizer que tudo isso transcorreu com sucesso. Criei um verdadeiro exército de engenheiros cidadãos que deram vida a projetos que defendem o interesse público, a engenharia e o desenvolvimento científico do país. Projetos que promovem o avanço econômico, cultural e social com ética profissional e determinação. Você pode não saber meu nome, mas com certeza conhece muitos dos meus feitos. Afinal, são mais de 100 anos de história que acumulam experiência, tradição e credibilidade em minha bagagem. Mas não se preocupe, minha missão de contribuir com o desenvolvimento da sociedade não envelhece, ela se renova constantemente. Atuo de maneira integrada, conectada e sem fronteiras geográficas. Meus eventos e reuniões podem ser acompanhados presencialmente ou pela internet. Mantenho meus associados atualizados por informativos e publicações colaborativas, que são escritas pelo verdadeiro protagonista desta história, você. Você pode não ter me visto nascer, mas saiba que contribuiu para que eu estivesse aqui hoje. Afinal, sou feito por pessoas. Se já me conhece, é associado ou contribui com a minha causa, o meu mais sincero obrigado. Se não me conhece, tenha certeza, minhas portas estão abertas para novos associados que tenham o desejo de escrever novas páginas desta história. Apesar de ter nascido no passado, sempre atuarei por um bom futuro. Muito prazer, somos o Instituto de Engenharia.
Senhores, boa noite a todos presentes no canal do YouTube do Instituto de Engenharia e conosco na plataforma oficial do Instituto de Engenharia. Aqui estamos pela divisão de estruturas, no qual eu e o Douglas estamos representando, assim como o IBRACON, em conjunto, em parceria com o Instituto de Engenharia, eu como diretor do IBRACON, e o Douglas também representando o Instituto de Engenharia, em parceria hoje também com a ABSIC, Associação Brasileira de Construção Industrializada. Trazemos hoje a palestra internacional do professor Atorod Azizi Namini, né? Eu vou fazer uma breve introdução do professor e, posteriormente, nós vamos passar a palavra a ele. Tá? O professor Atorod é engenheiro civil formado pela Universidade de Oklahoma, doutor em engenharia pela Universidade da Carolina do Sul, em 1985. Professor Vassan Surti, de engenharia civil, chefe de departamento de engenharia civil e engenharia ambiental da FIU, Florida International University, diretor do Centro de Transportes da FIU, para o sistema ABC, Accelerated Bridge Construction, desenvolveu diversos projetos estruturais de pontes que estão sendo implantados nos Estados Unidos atualmente e também internacionalmente para o mundo afora aí. Premiado com o título de professor emérito em engenharia do diretor do Centro Nacional de Pesquisa em Pontes pela Universidade de Nebraska-Lincoln até janeiro de 2011, foi premiado também com o título White House Champion of Change, Transportation Innovator, em 2015 pelo governo federal norte-americano. Escreveu diversos artigos, mais de 200 artigos técnicos relacionados à engenharia estrutural e pontes, né? Bom, apresento a todos o professor Atorod. Atorod, can you hear us?
Yes, I can. Yes, I
Okay.
can. All right.
Well, the speech is yours. Thank you very much to be with us this night, Atorod, again.
All right. Okay, thank you. Thank you for inviting me, and good evening to all my Brazilian friends. I've had the honor of being in Sao Paulo with Rafael a couple of times, and as soon as the COVID-19 is over, Rafael, I'll be up there again. So
yeah, and I'm going to be here to be with you again in Miami. We hope so. We get together as soon as possible, Atorod.
Oh yes, of course. We'll hopefully this will be back to some level of normalcy. So let me pull my presentation, and
yes, of course,
we get this started. And I'm gonna go a bit the slow, so please take a note. If you have any questions, we'll try to answer any questions you have. At the very end, I'm also gonna have my contact information, so in case that if you like to contact me through email, you will have my email address. So what I will be presenting to you is ultra high performance concrete based solutions for bridge design and retrofit and so on. Ultra high performance concrete is really catching on in the US. It's really UHPC for abbreviation, we say. It is first found its application in the bridge. Right now, actually, we do have some projects. We are looking at using the UHPC for high-rise buildings. But today, I'm not going to discuss the high-rise buildings. I'm going to just focus on the bridge and applications. At the very end, actually, I have some couple of topics that I'm going to show you that is not UHPC, but it's very much related to ABC and very much related to the bridge engineering. So with that, let's get it started. So first of all, I just got the gist of it. I don't speak Portuguese. I wish I did. I think Rafael was mentioning about our center that is dedicated to the ABC. So since 2013, we have a center that is called Accelerated Bridge Construction University Transportation Center, and funded by US DOT, is dedicated to bridge engineering and developing ideas, concepts, solutions for ABC implementation. So FIU is a lead, and Iowa State University, University of Washington, University of Oklahoma, University of Nevada, Reno are our partner universities. So it's a big organization, and approximately we get about $1.5 million a year to conduct research among all of us. And I am the director of the ABC UTC. And remember this website too, okay? abc-utc.fiu.edu. You can find lots of information. If there is time, I can probably go to that website and show you a few things. So UHPC, don't worry about all the material in this slide. UHPC is there is a company that is really marketing this. So you probably have heard, and I'm not going to mention the name, but company that is marketing this thing in the US, and the price is very high. So at the ABC UTC, we decided to develop a mix, UHPC mix, that everybody can have it. Okay, so there is a major project, and if you go to our website, we published our progress in there. And within the next few months, we are going to have a workshop, basically online workshop, and I will make sure that I will pass it to Rafael. So if you are interested to participate, it's going to be free, and anybody around the world can participate. And we are going to provide the instruction on how to make the UHPC, that you can make it yourself using your local material, and you don't have to pay such a high prices. So this is just a chart saying that I'm coordinating this project for developing a so-called non-proprietary UHPC mix or ABC UTC mix. And then the principal investigator is Royce Floyd, actually from University of Oklahoma. And they're doing, and I will give Rafael, I will give you the PDF copy of my slides so everybody has it, okay?
Okay, no problem, Atorad.
All right.
Thank you very much.
You bet. So there are, over here, basically this slide says who is doing what in developing the UHPC, non-proprietary UHPC, okay? And there are lots of testing that they are doing, just a material testing, trying to optimize it and so on, okay? And there are also, for example, different universities in our consortium. They are doing a structural testing too. So they are developing the mix, and in order to select the mix that they say that really should be used, they're also doing a structural testing, like for closure joints or a bond test and so on. Shear test, for example, University of Washington is doing some shear test and so on. So the UHPC mix that we are developing, that is going to be available to anybody that wants in the world. It is going to also, we are making sure that its structural property is adequate. We are doing lots of durability, rapid chloride permeability, freeze-thaw, and so on. I just wanted if you go to our website, you will see more detail. If you are interested, for example, how to make a UHPC mix, I mean, this is the kind that tells you, for example, per cubic yard, how much cement do you need, how much slag, silica fuel, and so on. Now, you can play with this. You can start with this. This probably will give you somewhere around 56 days. Probably it's going to give you 20,000 PSI strength. But if you want more than that, then you need to beef up your amount of the cement and the silica fuel. But this is a kind of mix that you can basically start, okay, play with. And I can tell you the biggest cost is the steel fibers. Steel fiber is a major cost. All right. The durability aspect, the main reason why we are using the UHPC is because of its durability aspect of it. So it is so dense that nothing penetrates through this material. And that's what the advantage is. Also, it has a tensile capacity. And after you form a crack in the tension side, it's not the end of the game. You can get the strain hardening and so on. So this is a very busy slide, but what I would like you to do is just notice one thing. This chart is UHPC, and this chart is just a normal strength concrete. Okay. Horizontal axis on both of them is a number of the days that the samples were exposed to a salt water. Okay. The vertical axis is, just imagine that's the level of the corrosion that is taking place. Okay. So after 450 days in the UHPC, you will see that very small corrosion activity. But in normal strength concrete, several times of that. So UHPC, the durability aspect is the main thing. And because in our bridge structures, we do want to have a very durable material so nothing penetrates through it. Okay. And we've done, lots of other people have done lots of work with the UHPC too. So it's an extremely durable material. Okay. Now let's come back with and discuss the application. Okay. So from this point on, we are going to discuss the application of the UHPC. Okay. One of the areas that is of interest to us is if you have a prefabricated, let's say, column, prefabricated cap beam, like here, for example, here is a bridge. This is the column. This is a cap beam. Now you can prefabricate this, and you can prefabricate this. You can bring it to the side and then connect them together. Right now, there are lots of connections that's available. Most of those connections are basically just making a hole and then going through. So if you make a slight mistake, and if everything doesn't fit, then you are in a world of trouble. Okay. So there are also these coupling that you can use in order to connect them together. Again, these are not cheap, and it's a very, you have to make sure that everything fits. And if it doesn't fit, then you're in trouble. This is so-called you make a duct, and then you pass the reinforcement, and then you fill it. Again, the tolerance is very important in this connection. This is another one, the so-called the pocket. So you make a hole in the cap beam, and then you bring the column, and then the reinforcement goes, and then you fill it up. When you do this kind of stuff, that takes a space, so you have to shift things around. In the real structures, you have lots of reinforcement, and this doesn't go very well in the practice. There's another one that we call a socket. Okay, there's a pocket, and then there's a socket. So socket is basically you make a hole, and then you just insert the column inside of it. All right. Again, in these cases, you have to push the lots of reinforcement to the side. Okay. For example, here, as you can see here, for example, in the real structures, if you want to put some kind of a, let's say, tube inside of that, it's a very congested. It's not very easily done. And here you can see, if you make slight mistakes, and if things doesn't fit, this is fine. But if it doesn't fit, then there's a problem. Okay. So what we did, we said, okay, you know what we are going to do is just bring the reinforcement out of the cap beam, have your precast column, and you have the reinforcement, and then splice it with the UHPC outside. There are many advantages. This detail works for seismic and non-seismic, because in the seismic areas, this area is so strong that it remains elastic, and the plastic hinge forms outside that. Okay. So we did lots of testing. Here it is, for example, precast column, precast cap beam, and then trying to overlap them. Okay. And here it is, you can see it. So we tested. Here is and damage is always outside the connection area, and that's what you want, right? Because that's what, you don't want any damage in the connection area, and this kind of detail achieves that. Okay, here is a number 5 bars, number 6 bars, and this is just normal strength concrete. Okay, so our design criteria is very simple. The length of the splice is only 8 times the diameter of the bar. So that's this length, overlap, splice length. The other thing is that, see, now you don't have to worry about the tolerances, because this thing, you just connect them together and you fill the with UHPC, so you don't have to worry about the tolerance. Now we do have procedures on how to, in the field, for example, hold the cap beam while you pour in this. So that, I'm not showing that over here, but the contractors can come up with many different ways too. But we do have one way that we have suggested. Another big area that is really attracting lots of attention, okay, is retrofit. Okay, I'm pretty sure in Brazil you have same probably concern, okay, because there is not that much money to replace all the deficient bridges. We have to retrofit, we have to repair most of them. In the US, we have the same problem. You cannot replace every bridges that are deficient, every bridge that shows corrosion, this kind of corrosion and so on. You cannot replace it, you have to retrofit. UHPC is a wonderful material for retrofit. And I think over the next several years, you're going to see UHPC's most application is not going to be for new bridge, but it's going to be mainly for retrofit, upgrade, strengthening, so on. And I'm going to show you some examples, okay? Now, this is not new, okay? Those of you who have followed UHPC, these are some photos I got from my friend, Professor Eugene Bruweiler in Switzerland, and I visited him a couple of times, and we are exchanging information right now. So these are photos that, for example, that some rail type bridge that they just basically just wrapped it with the UHPC. And the end product is much stronger than the original, and it's durable. So this is an extreme example. We can do a bunch of other things with the UHPC. For example, let's say a column. So, I mean, right now there are a number of different ways that you can retrofit columns, like, let's say, wrap it with a steel jacket, okay, or concrete. But UHPC is really, in my opinion, is a way to go. So we built many test specimens, and intentionally we introduced some damage, okay? So here it is. Basically, we said, okay, we casted the column, but then we left part of it uncast. And in fact, we spliced some rebar, assuming that some rebars are going to be corroded. And so we're going to have to cut it and then splice it. Okay. So what we did is that we filled this region with the UHPC, and then we tested. Now, you have to be very careful with this thing, because the material is so strong that the failure take place outside the region that you retrofit. Okay, I'm going to show you some numbers. And then once we fill this region that you see with the UHPC, we filled it using this kind of formwork. Okay, and you can come up with a number of different formworks, I mean, to do the job. But using a formworks, I mean, this type of formwork, we filled it with the UHPC. And then we subject it to different loads, okay? And this is the results, okay? Now, here is a retrofitted area, and the damage is outside. Now, you got to be very careful with this, because, see, these two specimens, we retrofitted here, but we didn't do anything to the foundation, okay? So where the UHPC is touching the foundation, that UHPC is going to crush that concrete. So the solution is that if you're retrofitting, you also have to retrofit maybe part of your foundation, or let's say the slab that the column is sitting, because that UHPC is so strong that when you apply load, it's going to crush that normal strength concrete. Okay, so you're going to be careful. The other thing is that you just have to, it's a very simple, you have to do some sectional analysis just to make sure you know what the moment capacity is here, what the moment capacity is here, what the moment capacity at the junction. So you can design it so that the failure is at the cross section that you want. And it really doesn't take much UHPC thickness like it. This is a 12-inch diameter column. Only 1.5 inch UHPC causes the failure mode to go from the repaired area back to top of that. So it's a wonderful material, and you don't have to use too much of it. Yes, material is expensive. Now remember, we are developing it's not developing. We have a non-proprietary UHPC mix that you can use. Even you can use in Brazil, using your local materials and produce it. It may become expensive because of the steel fiber, but you don't use that much of it for retrofit. And it's a wonderful material. Another thing we have played is flexural beams. Okay, flexural beams, if you don't want to go too much, you have to make sure that the UHPC that you put around the flexural members, they get composite action with the normal strength concrete. Okay, if you remove enough concrete, okay, that you get to the level of the reinforcement, then you don't need any mechanical devices like a stud or anything like that. Just wrap it with the UHPC, and that UHPC is going to bond to that reinforcement, and you'll be fine. But if you want to put a very thin layer, you may need some mechanical devices. Make sure that the UHPC and the normal strength concrete is acting compositely. The other thing that is important here is that you do not have to remove all the contaminated concrete. Okay, let me repeat that. You do not have to remove all contaminated concrete. All you have to do is maybe remove about 1 inch contaminated concrete beyond the reinforcement, and that's it. And the reason for that is because when you go only 1/2 inch or 1 inch beyond the reinforcement, okay, that UHPC makes basically what it does is protects the reinforcement from the both sides. Okay, so that's why you don't have to remove all the contaminated concrete. We have done some durability tests, and this UHPC, it chokes the system. Okay, it doesn't let to have the air and the water at the same time, so the level of corrosion goes down with these things. There is those people who know about the halo effect or halo effect, okay, that says you fix here, then the corrosion is going to be more on the other side. We've done those kind of tests. There is no halo effect. There is no halo effect using the UHPC for retrofit. Okay, so here is some of the stuff that you can use, for example, for retrofit right now. But forget about all that. Use the UHPC. Don't use the FRP. Don't use the steel jacketing or concrete jacketing or patching, something like that. So we've done lots of work. It's on our website. You can take a look at it. What we did in our test specimen, we used the sandblast to get an exposed aggregate. Now, that's very important. If you want the concrete to attach to the UHPC attached to concrete, okay, what you need to do is expose the aggregate and then wet the surface for 24 hours, okay? You can't just say right before the casting UHPC, you cannot come back and then just take a hose and then just hose it. That's not going to do the job. what you have to do, get an exposed aggregate, and then wrap it with a wet burlap and keep it for 24 hours. And that will allow basically the moisture to penetrate in the normal strength concrete, because otherwise there is a very little water in the UHPC, and that dry concrete is going to soak everything out, and then you're going to get cracking. Okay, so that's a very important aspect if you want to use a UHPC for retrofit. Here are some of the tested specimen we have tested. Okay. Now the other thing that we did, it's very interesting. We have not tested this one yet, but about a year ago, we took a beam, a rectangular beam. Okay. And we said that, okay, now we are gonna 2.5 inches. We put some reinforcement, and the top is 2 inches. The side is 1.5 inches. There was two objectives. One is we wanted to see whether we can cast the UHPC, and the UHPC is going to go all the way around. And then after that, we are doing lots of corrosion stuff, trying to see an intact bond between the UHPC and basically the existing concrete. We did one more thing, very interesting, because remember, I wanted to see whether the UHPC that we are going to wrap can go through a small space. So what we did, we built a formwork out of a glass. So the formwork is out of a glass. And then here it's a wet burlap. Make sure that 24 hours it's wet. And then we put the T-beam inside the glass formwork. And then we put the UHPC on one side, and we wanted to see if it goes all the way around. Okay. And here is it. Here is the result. Okay. And in fact, we had a two mixer, and one of them broke during the casting. So it took us 6 hours to cast this. And it was good because it was a good test. Everything bonded together, even though it took us 6 hours to cast it. Okay. So you see how everything is basically flowing. There was no honeycomb. This UHPC was going through that small space, because in UHPC there is no coarse aggregate. Okay, it's all sand. It's like very fine sand, and that because of that you don't get any problem with getting a honeycomb and things like that. There's another very interesting feature after we remove the glass formwork. The surface is just like I would say, just like a glass. Okay, so it's a really wonderful stuff. So here you can see. You see how the UHPC is coming up? So we are pouring from the top, and this thing is just coming up very nicely. And that's the finished product. So no problem. So it's a wonderful material. You can wrap the whole beam in the UHPC if you want to. And here is an interesting one. Okay. That T-beam that I showed you before the retrofit, this was the capacity. This is just a calculation, but I'm pretty sure that if you test it, you're going to get the same thing. Okay. And if you just cast it, okay, if you just cast it using this much UHPC and that much reinforcement, see how much the strength goes up from here to here, more than double. So that's why you don't use too much of the UHPC, but then the strength gain that you get out of this material is amazing, amazing. Okay. So that's some of the retrofit. We also have a very interesting concept. When you want to build structures, I think I have it here. Okay. So what do? We usually have a formwork, right? You have a formwork, you build the formworks, and then you put the steel cage inside, you let it cure, and then you have to come back and then remove it. That's a very costly process. It costs labors, it costs time, interruption to the traffic, some bunch of stuff. Okay. So what we have done and it's a new technology we are developing. Our formwork is made out of UHPC. So we have a formwork, let's say for a cap beam, formwork for the column, and then you bring it, you stack them on top of each other, you put the steel cage inside, and then you fill it with a regular concrete. Now you can also actually fill it with the lightweight concrete. Why? Because if the shell is made out of UHPC, nothing penetrates through it. So therefore, I can use a lightweight concrete. I can make my section smaller. My total weight is going to get smaller. My foundation size is going to be smaller, and so on. So this is a conceptual, just a cartoon that shows what we are doing. And here you can see, basically, here is the, basically you bring your basically the shell for the column, and then you can stack them, and then connect them, put the steel inside, and then fill it. So you don't have to build the formworks. You have something that is going to last many, many years, and you don't have to remove anything after you cast it, okay? And these are examples. Okay, so we have built. Now the challenge is that you got to make sure that there is a good composite action between the concrete that you put inside the shell and that shell itself. Okay, so we did some experiment and we solved the problem. The first experiment that we did was you can see here, we built a UHPC shell for this cap beam, and then we put this, you see this ridge. So we thought that, okay, if we put this ridge and we put a normal strength concrete, we can get a composite action between the two. Okay, so we built one that was just, the whole thing was made out of a normal strength concrete, and then another specimen had a UHPC shell and then filled with the concrete. Okay, so this is two specimens. One of them is just pure normal strength concrete. This one is a UHPC shell with the normal strength concrete. Okay. Now the difference is that, first of all, in this case, remember, for this specimen, we put these ribs. We thought that ribs is going to give a composite action. That was not the case. It didn't. And as a result, we had one big crack in the middle, but still we had a higher capacity. And you see, if I look at this specimen from the bottom side, from the bottom, see what you see. What you are seeing is the top. Okay, if I go to the bottom, look at, you can see that normal strength concrete is separated from the UHPC shell. Okay, so that ribs doesn't do the job. You have to do something else. So in order to, the material that you pour inside to get a composite action with the outside shell, you have to put some normal, basically some mechanical devices. So if you want to cast a normal strength concrete against UHPC, you have to use mechanical device. Okay. If you want to cast UHPC against the normal strength concrete, all you got to do is just have an exposed aggregate like I showed before. So there's two different type of problem. If you want to cast a normal strength concrete against the UHPC, you need a mechanical device. If you want to cast a UHPC against the hardened normal strength concrete, just get an exposed aggregate. That's all. Okay. So those are two principles that you have to be watching. And here, for example, so in one specimen, we build the shell out of UHPC, but then we put these mechanical devices, and then we put the steel cage, then we pour the concrete. And we test it. Now we got a good behavior. The UHPC shell and normal strength concrete behaved compositely. Okay, and this is the behavior. This is a beam, same size beam. The normal strength concrete is a low deflection. This is a UHPC shell filled with the normal strength concrete. You can see that you get a very ductile behavior, you get a very higher capacity, and so on. So I reached a 60 versus about 35 kips in this case. So that's it. This is what we call is a it's really ABC. It's an accelerated bridge construction concept, because you bring these shells to the site, you stack them on top of each other, you fill it with the concrete. There's no formworks, and then there's no maintenance because UHPC doesn't let anything to go through it. Okay, so it's a wonderful ways of doing it. We have some solutions, for example, for short span bridge. So you build a formwork in this shape, and then you can bring these, put them side by side, put the reinforcement, fill it with the concrete. And we build some of these modules, actually. We built some of these modules, filled it with the concrete, and then test it. So everything works fine in this case, okay? So the other thing, for example, with this concept of the formworks to be out of a shell, we played around with the, for the UHPC, for the column. So what we do is we have the shell made of UHPC. You put the reinforcement, you put the shell on top of it, and then you fill it. And then we have some details for the connection of how to connect this to the foundations, okay? Basically, the reinforcement comes out like this, okay? And then the reinforcement that's inside, and then there's a ring that's made of UHPC. And that's how you basically connect the shell to the foundation. Here, as you can see, that one of the test specimen, the reinforcement is coming out, and then there's going to be reinforcement inside, and then they're spliced here. Okay. What you want is that you want the failure mode to be outside. Now, in the first specimen, we didn't have any reinforcement in the UHPC shell for the column. Then the next one we added. So you have to have some minimal reinforcement, just a skin reinforcement, basically, okay? But the connection works fine. And everything, here is a load deflection curves, basically, very nice. Now, if you have a long column, it will be difficult to make a very long UHPC shell, okay? If you have a long column, what you can use is concrete filled tubes. Okay, so steel tubes, and then fill it with the concrete, but then connect it to the foundation, use the shear stud, and then these rings right here. Okay, so here is a detail. Reinforcement comes out, steel tubes sits over here, and you have some reinforcement in the column, some reinforcement here, and then you splice them with the UHPC. And we've done some tests here. You can see. Let me see if I think this one is a. You can see that, and the failure is right at over here. And this is a typical type of failure that you get with the concrete filled tubes. Okay, you see this right here, right? It's like, it's a bulging, really. It's not buckling. It's the concrete inside crushes, and then steel yields, and that's what you get. Okay, so if you have a very long column, I don't know, 20 meters or whatever, just use a steel tubes, but then you can use a UHPC shell for a cap column. And here's another one. Okay, these were tested, fortunately, before the COVID-19, because we are actually right now, we are in the lab, we are working, but we have to have no more than 2 people, 2-3 people at the time in the structures lab. So it's been kind of disruptive for us. And this is it, basically. So the connection works. So you can, again, everything that we do, all the connections, everything we do is connecting everything using a UHPC. And that's what I'm saying. Even the material is expensive, but you don't use too much of it. You don't need to. And here is some shots that the failure is right outside of this connection area. Okay. All right. Every day we try to find some applications. Okay. So in US we have lots of bridges that have used the timber piles. And I don't know in Brazil you have it or not. Rafael, do you guys have lots of bridge with the maybe piles using the timber piles, wood piles?
Yes, we use a lot of wood here in Brazil.
Okay.
Also.
For the columns, for the
Yeah. No, for all the bridge.
okay.
In the outback part of Brazil, like Pantanal, or in the center part of Brazil,
Okay.
some roads are there are bridges that just use wood. So
Okay, good. All right. So stay tuned, Rafael, because I'm going to be asking you some question too. Okay, so pay attention. Okay, so don't fall asleep on me.
okay, no
Right?
problem.
All right. Okay. I know Rafael for many years, so that's why I'm teasing him a little bit. All right. I wouldn't joke with anybody else, but I know Rafael, so he knows me, so we play with this.
No
All
problem at all.
All right, Rafael. Okay. Now, what we there are lots of bridges that use the timber piles in the U.S., and lots of them are just ruined. I mean, there's a fungus, there is a insects, for example, and over time these things are just some of them are just gone. Okay, so what we are doing right now, we are developing techniques to retrofit timber piles using a UHPC. Okay, our objective is that we don't count on the existing timber piles, because if I put only very small thickness of the UHPC around that pile, okay, that's all the strength. I'm going to have more strength than original column. So we are using the existing timber as just a formwork. That's all. We don't, after we wrap it with the UHPC, we say, I mean, as far as we are concerned, there's no wood in there, okay? Because the portion of the capacity that comes from it is a very minimal. So I don't have too many slides. We've done lots of tests actually, but I don't have the slides right now to show you. So we are doing lots of stuff trying to see that how the interface shear works. Okay, I can tell you this much. Okay, the big lesson that we learned: if you wet the timber piles before you cast the UHPC around it, you tend to get a better behavior, because what happens when you soak the timber piles in the wood, in the water, it expands, okay, and then it contracts. Otherwise, if the wood is dry and you cast the UHPC, if the wood expands, okay, it causes a cracking, okay. So actually, our solution now is something else. We say, what I'm going to do. In fact, what we haven't done the test. We are planning to do. We're going to be wrapping the woods with some kind of soft material. Okay, imagine even a foam type material. So the UHPC will be cast against that soft material. So really, physically, that foam material, we can spray it probably. The foam material is sprayed on the wood, and then the UHPC is cast against that. Okay, so there's a very soft material between UHPC and the wood, and that will prevent the cracking. So you don't have to worry about the wood being dry or wet. Okay, so that's a major thing. So we've done a bunch of tests. Okay, try to put the nails at different angles, do a interface shear type test. So we've done a bunch of stuff, but our conclusion is that the best thing is just put some soft material, wrap the timber pile with the soft materials, and then cast the UHPC. Then you should be fine. So, and in the US, actually, the states that they have timber pile, they're very interested in this, because this is really providing us with lots of good options, effective options really to retrofit some of these bridges that have timber piles. Now shifting there's another thing in the ABC, accelerated bridge construction, the barrier system, okay? This barrier system on the side of the roads, that's important. So we have developed a connection detail. You can prefabricate this right here, this much of it. The deck is already there. The deck is already cast in place or precast panels, and then you can connect them with the UHPC. Now, I don't have lots of details, but if you go to our website, you can see the details. But the gist of the story is that we have developed a really neat connection detail that you can connect a precast barrier system to precast deck system with the UHPC. And this one is a really interesting one because as you see, the UHPC is going to be maybe a little bit above the deck, okay? And that's what you want, because during the snow, and when you're cleaning the snow, if you don't have this area, the water can penetrate at that junction, okay? So you have to have exposed aggregate here before you cast the UHPC, and that area is going to be sealed because this material, nothing penetrates through it, okay? So there's a lots of durability problem if you use a normal strength concrete, but with UHPC, you won't have that. Right? But anyway, so this is a very interesting solution. And in fact, this one is not updated. This area actually goes all the way to here, okay? If you go to our website, actually, you will see there's much more information on this. Let me skip that. I'm not going to say much about this right here. I won't. Some of you have seen, for example, there's this steel bridge system that is called the simple for dead continuous for live load. And it has a very complex, for seismic region, it's a very complex detail. And we are replacing all that with the UHPC. Okay, so it's I have one PhD student that's working in this area. So I won't say too much about that. If you are interested in this system, I can provide you with more info, or you can look at the website. All right, now let's look at the future. Okay, now what I'm going to tell you, it's not a science fiction. The robotics in bridge construction is coming fast. Okay, in US right now, the military is spending billions of dollars on using robots for construction. Okay, so they take a raw material to the field and then they print it. What we are doing now is that UHPC shell that I told you. Now imagine your formwork is made of UHPC. Now imagine one step further. We are going to print it with the robots. Now you're taking the labors out. It's going to be really fantastic. So what we have done, so here is a kind of cartoon, but this is a reality. Actually, we have the we have the system. So the idea is that we cast these things layer by layer. Okay. Now this right here that you see how we deposit this. Let me show you one of the. This is the one. What we have here. This is a chute. Okay. Now what I'm not showing you how the UHPC is being deposited. It's a chute that the UHPC comes over here, and it's a layer by layer fabricate the construction. There's a sheet over here that prevents it's like a cooking sheet actually, prevents the UHPC to stick to the site. You cannot see that, but there is a plate here that heats up to about 120 degrees Fahrenheit, 120, 125 degrees. So as we move along, let me see if I have a. As we move along, there's a heat over here, and that heat makes the concrete to harden faster. Okay, this is a small model just for the exhibit that we have. We are not there yet for a commercial, but it's coming. It's a very, it's not a brain surgery, but this application of the robotics is coming really fast. And over the next several years, we are going to be focusing on using the robots to build components of the bridge, because especially this printing is well suited for accelerated bridge construction, because you can print these large pieces on site. Okay, now here's the advantage. Okay, you are going to cut the cost of the transportation. I mean, there is no reason why we cannot print these elements near the final site of the bridge. Okay, so you don't have a transportation cost. You can use the local forces. You can use the local material. All you got to do, imagine that, for example, no, it's not reality right now, but it's coming fast. My feeling is that within the next 10, 15 years, we are going to be there. Now imagine you just ship these robots, this kind of robots that you see, and then you have the material in there. They can mix it, and they can print it, and there you go with the UHPC shell. There you go. You got the formwork, you stack it, you fill it with the concrete. You are done. Okay. So this robotics is coming fast. This is another framework that this one can move up, down. It can move horizontally. It's a 6 degrees of freedom, basically. So you can print any shape that you want. Okay. And at this point right here, you can put at the print head. The print head could be this right here that I show you. So anyway, I wanted to show you this one. Again, this is not science fiction. This is a reality. In the building area, we are doing really fast. The military in the US is spending billions of dollars. And one of the main reasons for military to spend the money for printing is because, for example, if they want to, by the way, you can print steel too, not just concrete, steel, plastic, whatever you want. One of the main reasons that the military is interested in this is because usually, for example, if they want to buy something, they have to buy not one, but they have to buy thousands of them. Okay. But with these printers, the supply chain, they don't have to buy 100,000. They can just print as many as they want, whatever they want. Okay. Now, again, remember, you can print steel components with these things. So these robotics, again, if I was a structural engineer, if you guys are, especially the ones that are in school, pay attention to it. These are the ways of the future that's coming up. Or, for example, the other thing that we are working on right now is, you probably have seen the shotcrete, but we are developing the robots that can go inside the pipe, basically. Inside the pipe, it can detect where the crack is, or just put a liner, UHPC liner, basically. Move along the length, and then put a UHPC. Or shotcrete. This shotcrete is really I think, is going to be one of the main application of the UHPC. Okay, it's even bridge overlay. Okay, imagine I have this kind of problems. Okay. Now imagine if I go back and with the shotcrete, I just spray, just like a hose, sprayed. Okay. We have developed a mix that is suitable. We have this specimen. In fact, we were supposed to do this thing back in the May because of the COVID-19 is postponed, but we are buying basically just a device so we can spray. So we're going to be spraying the UHPC on these specimens. And even some of the columns that, for example, we tested for retrofit, we have it ready. And then what we're going to do, basically, just spray the UHPC and then test it again, see what happens. Okay. So the shotcrete, this right here again, one of those things is coming fast. Europeans in Europe, again, I'm not going to name the company. I think that company is. They are looking at the more of a business standpoint, so they are acting like this thing is so difficult to do. It's not at all. The shotcrete with the UHPC is a simple thing to do. It's not that difficult. Okay, so we are working in that area. Hopefully, that should be available soon. I think that application for retrofit, because again, remember, we don't have that much money to replace every bridge that we have, whether in Brazil, whether in the US, or everywhere. And this shotcrete is a wonderful way of the basically the trying to use the for retrofit. All right. If you just give me just 1 minute, please, just 1 minute, just 10 seconds, please. I apologize. Okay. So that's a now the other thing that I was gonna let me go back here. Okay. So that's as far as the ultra high performance concrete. The other thing that there's two other technologies that I'm going to discuss with you. One of them is called steel. I talked so much about the concrete, UHPC. So just to be fair, and also give the equal attention, I guess, to steel. I wanted to share with you, I think Rafael knows about this system called the folder plate technology. But what Rafael doesn't know is that now we have a second generation of these things. What this system is for ABC. So what you do is you take a piece of plate, you bend it to a C shape, okay? This is a proprietary is a patented in the US. And if anyone is interested, I mean, we can help them to implement it. And then you use the brake, basically press brakes to bend these plates. The bottom is open, so it's a C shape. And the bottom is open in this case. And then you cast a deck on top of it, and then you ship the several of these to the side and then put them side by side, for example. And so far there's about 12 of them across the US that have been used. But up to now, everything is limited to 60 feet because the press brake is limited to 60 feet, okay? So you bend the plate, you galvanize it if you want for water, for corrosion, and then you cast it, you ship it to the side. You can build the formworks. You can cast a deck on top of it, and then you ship it to the side. You can pick it up with a crane, very light. It's not that much, the weight, and then you put them side by side like this, and then you join them over here. We have a much better closure joints detail nowadays. This is the first one that was used in Uxbridge in Massachusetts back in the 2011. It was open to the traffic in 2011. Okay, but nowadays there's 12 of them in service with the excellent performances. All right, now what the second generation is, up to now, the maximum length of this thing was 60 feet. Now we have developed a connection that we can connect them together, and we can go all the way to 105 feet. Okay. So here is a specimen that we built. No, this is not 105 feet. We wanted to test the connection. Okay. And then we did a cyclic testing, you can see. Now, this one was almost, I think, 5 million cycles. We applied the 5 million cycles. We started the test on September 12, 2019, and finished it on October 21st, 2019, basically 24 hours a day, that the specimen that you see down here was being subjected. Each time the ram move up and down, that simulated like a one heavy truck passing over. Okay. All right. So anyway, so that system is a just again to be fair to the steel, we had that. I showed the system for shortest span bridge, for simplest span bridge. Okay. And I think finally what I have before I wanted to show this one. This is a technology that we have, and I believe you guys have the same type of problem in Brazil too. Rafael, you do have bridges that you worry about how to inspect them for corrosion, right? Especially when the steel is inside the concrete, correct?
Yeah.
Okay. Well, if you have that problem, we are with a colleague of mine in Germany. We've been working. I've been working in this area for 20 years, and my colleague in Germany have been working 30 years. So 2 years ago, we decided to join our forces, state-of-the-art technology to inspect the status of a steel strand embedded inside the concrete. Okay. Now this technology is not for we are not really publishing all the details. There's the secrets of the trades, and we are discussing right now with the university to form a company, and we are going to be providing a service. There's many states in the US that are really interested in this technology. So it could be a parking garage, it could be a bridge, it could be a segmental concrete bridge, pre-stressed concrete, anything that you worry about. You say, okay, what is the status of the steel inside the concrete? Okay. So if you are worried about that, this technology for it. So we have actually this right here. This is actually from a real segment, and we are able to tell exactly where the defect is with the signals, even though there is a bunch of other reinforcement in there. Okay. And the technology really is based on it's just like an MRI. When you go to doctor, they look at your shoulder or your hand, your legs, or your head, or whatever with the MRI. It's the same type of technology. We use a magnetic field to investigate the response of the steel to the magnetic field. Now, what is complex about this issue is that in a real bridge, you have so many different mild reinforcement. Let's say in segmental concrete bridge, you have a mild reinforcement, you have tendons that has a metal duct, and then you have a steel strand inside, right? So, but what you are not interested in the status of those mild reinforcement. You are not interested in the status of the metal duct. What you are interested is the status of that steel strand that's inside the duct. So how do you isolate? It's just like an MRI that you section and you look at basically sections of the body section. That's what we are doing with these bridges. Okay. So I'm going to show you some examples. So we've done some tests in the yard with this, but we've also done some tests in the field. Okay. For example, here we had some segments, and they were taking this segmental concrete bridge out of service, and we brought several pieces to the lab, outside the FIU, and some of the ducts actually didn't have any steel strand in there. It was empty. So we were able to put some steel strand with a known defect, okay, and then use our technology trying to see if we can detect. And that's what I was showing this right here. Very clearly, we can see exactly where the damage is. Okay. Now, I'm going to show you something else. This is if I have a complete breakage. I mean, you cannot get any better than this. There was a bridge that we just recently, and we are going back actually August 13 or 14. We're going to test some more. And this bridge is made of, along this length, okay, along here are the these modules that you can see. This goes along the length, okay? These modules that are, there's a post-tensioning rod that goes transverse. This is a perpendicular to traffic, okay? Traffic goes toward the page, and then the post-tensioning rods is in the transverse directions, okay? So post-tensioning rod goes along the transverse. So a couple of them actually were ruptured, and we are able to basically say exactly, I mean, where these things are. Now, what we did recently, we built a full-scale model of this bridge, a segment of it, okay? We built a full scale, okay? And 3 of them, okay? We put all the reinforcement that there is, okay? All the reinforcement that there is. And then cast the concrete. And then put them side by side, okay? And this is it. This is like the traffic goes this way and the post-tension rod goes this way, okay? It's a full scale. You see over here, one of the holes has a metal deck and the other ones doesn't have, okay? And we put the holes in different locations so that test our technology. Now, let me show you some of the results with this. So we put some post-tension rods over here, but we put the damage, we basically put the damage, cut the rebar for 4 or 5 inches, simulating the corrosion, okay? And by the way, the cutting the bar section of it or just corroded is the same thing, because when it's still corroded, you have an iron oxide. It's a non-metallic, so it doesn't make a difference. But let me show you the results. So so imagine now I'm going to put a post-tension rod, and I'm going to put some damage, intentional damage on the post-tension rods, okay? And here's the signal. I mean, you cannot get any better than this. We are able to exactly say where it is. So this technology is applicable to both, let's say, parking garage or any steel element that's embedded in a concrete, and you want to know what the status is, this technology is available. I wanted to show this one because I know that Brazil is dominated by concrete structures, not so much by steel. And the corrosion is the main problem. There are lots of collapses take place because of corrosion. The bridge that collapsed in Italy a couple of years ago, that was because of the corrosion. And it happens more often than what you think. And I think we are going to see problems with our bridges across the world in the failing because of the corrosion. And this technology is really a state of the art in the world. There's nobody, what we have solved is that how do you section the structures and how do you zoom in the area that you want and wash out the effect of the mild reinforcement, okay? And this is it. You cannot get any better than this. I mean, I'm seeing exactly what it is. And if I take the x coordinate of this point, x coordinate of this point, subtracted, that's equal to thickness of my bridge section. So anyway, that's end of the technical. I hope that some students are listening to this presentation. Okay, there are some research opportunity, and I promise you, and I'm looking. We have lots of research projects. And I'm looking for some qualified PhD students, okay, that wants to come to Miami, not far away from the Sao Paulo, okay, and would like to work with my research team in the research. If you are interested, send me an email, okay? It's very simple, aazizina@fiu.edu. And then I promise if you send me an email, say I'm interested in your PhD program. And we do have assistantship too. So your tuition is paid and you get a monthly allowance. But if you're qualified, and you get fully admitted to the university, okay? So we provide that. And it's for the students, a comfortable living, the assistantship that we provide, send me an email, and then I promise that I will arrange a Skype. I'd like to interview my student before I even tell them to apply for to the university. Okay. So, Rafael, on that note, I'd like to conclude, and if there's any questions, I will be more than happy to answer.
Well, thank you very much, Atorod, for everything. For your presentation was awesome, was fantastic about all the new technology that you bring to us. Even this new technique to try to find some problems in the steel embedded in concrete. That's a problem worldwide, isn't it, Atorod?
Oh yeah, it's a worldwide. In fact, I won't name the bridge, but recently in Florida, you saw that there was on the news that major segmental concrete was closed. And really,
yeah,
the only technology, this is the only technology. So we were up there and then we were helping out.
Yeah, we received some news from Florida that new bridges were like the pump station cables or the pump station tendons were injected with how can I say that? Yeah.
Sika cement. It was the story on that one was that there was a major problem with the bridges, segmental concrete bridges that were built back in the 80s.
Yeah.
The first generation. And now the ASB has done very good job. So now we don't have that problem. The way they were grouting this duct, it was not, the quality control was not there.
Mm-hmm.
So in 2000, they started using another proprietary grout. But then in 2010, we found out that some of these things, after 10 years, has not set.
Mm-hmm.
And it's causing. So we do have one faculty that is working on the material aspect of this problem, Dr. Kingsley. But what I'm concentrating on is trying to locate where the corrosion is. Basically.
Yeah, but when you find the corrosion on tendons, what do you do? That's the $1 million answer worldwide. Yeah. Nobody knows what to do. That's the main problem at the road.
Exactly. That's somebody else's problem. My job is to find it. My job is to find the problem. But what they do is, for example, they have a segmental concrete bridge that in Stuart, if you Google STUART. Mm-hmm. So in that case, what they do, usually this segmental concrete bridge, they have these tours, and I guess they predicted that someday they may have to put additional post tensioning. So they are putting more post tensioning in there just to be safe.
I know.
But in parking garage, sometimes you just have to replace it. But knowing the problem, at least if you know that you have a problem in certain areas, that's good. The only thing that I can say is this. Sometimes we've seen it. Let's say you have a duct, okay? And you may have the moisture, but you don't have the air. You don't have the oxygen in there. In order to have a corrosion, you have to have a water, and you have to have an oxygen.
Yeah.
If you have one of them and not the other one, you don't get the corrosion. Okay. There has been some cases that they have opened the duct. Now you've got the moisture and oxygen. Now in a couple of weeks, you've got a major corrosion. So you got to be careful. So this non-destructive technique, it's a non-invasive. So we don't drill a hole or anything. We just go and magnetize and then look at the signals and then say, okay, these are the maybe problem areas. And then if it's extensive, then you can do something. The other application of this technology is you can, let's say, for example, you can magnetize and you can take a signal, let's say, on day one, let's say today. Then you may come back, let's say 1 year later, do the same thing. And if there's no change in the signal, it means that whatever is there may be corrosion that took place, but it's there. It's just stopped. So you have some section loss and you don't have anything that progress.
Okay. Yeah.
So that's another way. What we say is that you get the base signals and then you monitor your structure over the years just to make sure that there's no change in the base signals.
Mhm. So, Douglas, do we have any questions from the public or from you?
I'm checking here. No, we don't have nothing for
Just in
that.
português, quem quiser fazer as perguntas mesmo em português, nós podemos traduzir, translate to Atorod, ou traduzir para eles, e a partir da resposta do Atorod também transmitir, traduzir para todos em público aí, quem quiser fazer alguma pergunta. Tiago, nós temos alguma pergunta no YouTube?
So I have my email address too. So if somebody
Yeah,
wants
of course.
to,
Of course.
we can update
And about, it was very interesting about the connection that you use for the barriers on the bridge using UHPC. So did you do any crash test for this barrier, for this connection?
No, that's a phase one of that. So we've done so far numerical, and but we are building right now a specimen that we are going to do static testing, and then we are going to do pendulum, and then go to crash testing after everything is proven, because crash testing is very expensive. So we are doing we've done numerical, we're going to go static testing, and if the static testing is passed, then we go to the pendulum testing, and then after the pendulum test, if everything works out, then we're going to do the crash testing. But we are looking for we are looking actually for a funding from the Fed, trying to see that, because that's a very expensive. It costs a couple of $100,000 to do just the crash testing.
Okay, that's good. Douglas, alguma pergunta?
I have one from YouTube. They are looking to know if you have a specialization course at Florida University.
What kind of course?
On specialization, not I believe on lato sensu, not PhD or Master of Science.
We do have I am teaching a bridge engineering class.
Okay.
That's online, so anybody around the world they can take it. So if somebody is interested to learn about bridge engineering using a AASHTO LRFD, they can send me an email and I can put them in contact with somebody that can walk them through.
Okay. We have another from Zoom, from Camila Queiroz. She would like to know how was made the surface prepared to concrete of different and ages and different properties.
Okay, I think what she's probably referring to is, sorry. I believe, let me share my screen. So I believe what she's referring to is, when you cast, okay, here it is, okay? Yeah. When you cast and this is what I was saying, high strength UHPC against the normal strength concrete, you have to make sure that the aggregate is exposed. You have a roughness, okay? The aggregates are exposed and rough, and then more importantly, you have to make sure that the surface is wet. And if you have a exposed aggregate, you really don't need these. You don't need anything else, okay? Just make sure that if you want to cast a UHPC against the normal strength concrete, make sure the aggregate is, so when you touch it, and this is how we use, you see a pretty rough surface, okay? You can just walk your hands on top of it, and then wrap it with the wet burlap. Let me show you. This right here, okay? For example, here, you wrap it with the wet burlap. So this was the concrete. You wrap it for 24 hours. You have to make sure that the surface condition of the normal strength concrete, It has exposed aggregate and also is wet. And then if you do that, then it's fine. So this is casting in UHPC against normal strength concrete. And what I was saying, if you want to cast the normal strength concrete against the UHPC, then you need the mechanical devices because you won't get the composite action. So it's two different problems, completely two different problems. But the level of roughness is not that much. It doesn't matter what kind of concrete you have. Just make sure the aggregate is exposed. That's all.
Okay, the shear friction is better with the aggregate exposure.
Yeah.
Okay.
It gets a really good bond between them. And the failure surface, usually it's not at the interface. The failure surface is away from it.
Yeah, it's the same what we do with a regular concrete. And the preparation of surface is the best way to assure the perfect interface.
Correct.
No?
Right, exactly.
Okay, we have another question. Do you have studies about the effect of delayed heterogeneous formation in UHPC?
Delayed, could you repeat that?
Delayed heterogeneous formation.
Okay, I am not a material person. I think I know what they're saying, but that's a question that probably a material engineer probably can answer. I'm not sure exactly what aspect they're referring to, but I get the feeling that they're asking a very detailed question about the material aspect of the UHPC. Okay. I'm not a material person probably to provide a good answer for that one.
Okay. Let me see if you have more questions. Okay. I have one mine. Do you have some experience with underwater powering with UHPC?
Oh, good questions. Good questions. Very good questions. Usually we are retrofitting columns, but in the dry land, not inside the water yet. Usually the splash zone is a problematic. Pretty much have to build a coffer dam, okay? But we have not applied below the water. I know what they're asking for, and that's a good question. Usually the problem is below the water, you don't have the oxygen, it's just the water. The splash zone is where you get the dry and wet cycles, but we have not used UHPC under the water. No, we have not used, but I think it can be done. It can be done, but cover them.
Okay, very good.
Well,
Rafael?
Não, Thiago, nós temos alguma pergunta mais do YouTube ou podemos encerrar?
So I'm going to put my slide over here
Of
because
course.
I'm trying to recruit some PhD students. So if anybody is interested, make sure there's lots of exciting project.
I'll send an email after the presentation.
Okay. All right. Okay.
Yes, we have a question. A guy wants to send you an email afterwards to do a PhD with you.
Okay, send it. And I will arrange a Skype. We are looking for. It's a big team that we have. It's a huge team. And by the way, if it's the bridge engineering at FIU is probably in non-seismic and we're doing some seismic. It's probably top 2, 3. If it's not number one, if it's a top 2, 3 in the US right now because of all this US DOT designation that we have got. And it's a Miami, of course, a nice place close to Sao Paulo.
Yeah, it's an 8-hour flight.
Yeah.
Is it 8 hours?
Very close. It's very close,
Okay.
very close.
Right.
We have another question here, Aturad, from Cesar Dyer, is a professor from also the board of director from Ibracon. So he's asking you about if you develop or if you do a specific method for mixing design of UHPC.
Okay. I would put you in, imagine that, for example, he's asking using a local material, how you should start, what you should do.
Yeah.
There is a base mix that I showed you, okay? That you can probably use that as a starting point. This mix that I showed you. But if he sends me an email, I can put them in contact with Royce Floyd at the University of Oklahoma. There's also, let me show you one more thing. Maybe that's it. Okay, so I'm gonna show you, make sure that if you go to this website, okay, and I'm gonna show you where to find that.
Of course.
So this is our website. If you go under research, go under the OU research projects, okay? And then there is a project here, development of non-proprietary UHPC mix. And if you look at the June progress report, here you will see that there is a procedure that is outlined on how to go about to develop a basically UHPC mix, okay? And I can put you, if they can send me an email, I can put them in contact. But these are the, for example, some of the tests that you have to be running, and the STM test that you have to do. And then here is the mix itself, okay? That's a base mix. There's also lots of, let me see, you guys. There's also, we have in our website under the resource, I don't know, I hope that you guys see this. On the FHWA, do you see the page that says FHWA? Okay, all right. If you go to this page under the resource, FHWA, you will see under publications, and I'm giving you this right here because this is for the mixed development implementation industry subcommittee sharp project, sorry, FHWA, okay, technical notes, official UHPC website. If you go here, there is a, and I think under the publications, okay, under the publication, there is one publication that's properties and behavior of UHPC class materials. And tell me, do you see the PDF file opening?
Yeah.
Okay. Yeah. This right here is a very good publication. You can look at this one. This one can give you, can walk you through a bunch of stuff. So there is a tremendous amount of information that's there.
That's very good. Well, do you have any codes developed from UHPC? Yeah, because here in Brazil, the codes are they are limited to 80 megapascals. It's about 11, 12 KSI. I don't know the codes in the ACI from US. They are limited to what strength?
Usually, I mean, we are about the 10,000 PSI. 75, 80 megapascal. There is no national code. The best reference is the Federal Highway Administration has some publications that use that. Everything is in the, but there are efforts with the ACI trying to develop that. I think it will happen probably the next few years. But at the moment, no, we don't have anything that just like ACI 318, for example, for the UHPC.
Okay. I think we finished now, Eterod.
All right.
Wow, it was a tremendous pleasure to be with you this night. And well, again, thank you very much for your time.
Well, thanks for inviting me, and look forward, hopefully the COVID-19 go away so we can see each other.
Yeah. We have to play soccer again, my friend.
Oh yeah, that's right.
It was a pleasure to be with you.
Same here.
Douglas.
All right.
Thank you, Eterod.
Okay.
Hope to see you soon.
All right. Thanks a lot. Okay.
Thank you very much.
Bye bye.
Pessoal, boa noite a todos. Muito obrigado por estarem conosco e esperamos vocês nas próximas palestras. Muito obrigado.
Obrigado.
Bye, Atorod.
Bye bye.
Bye-bye.
Quando minha história começou, você ainda não havia nascido, mas eu já pensava em você. Apesar de não ter fins lucrativos, carrego uma missão ambiciosa desde o meu nascimento: promover a engenharia em benefício da qualidade de vida da sociedade. Este comprometimento com o desenvolvimento do país me fez começar a utilizar o meu espaço para gerar encontros e conectar pessoas. Como fiz isso? Abri minhas portas para reuniões no âmbito das divisões técnicas, reunindo associados voluntários das mais diversas áreas, a fim de realizar debates, estudos, seminários, cursos e palestras. E posso dizer que tudo isso transcorreu com sucesso. Criei um verdadeiro exército de engenheiros cidadãos que deram vida a projetos que defendem o interesse público, a engenharia e o desenvolvimento científico do país. Projetos que promovem o avanço econômico, cultural e social com ética profissional e determinação. Você pode não saber meu nome, mas com certeza conhece muitos dos meus feitos. Afinal, são mais de 100 anos de história que acumulam experiência, tradição e credibilidade em minha bagagem. Mas não se preocupe, minha missão de contribuir com o desenvolvimento da sociedade não envelhece. Ela se renova constantemente. Atuo de maneira integrada, conectada e sem fronteiras geográficas. Meus eventos e reuniões podem ser acompanhados presencialmente ou pela internet. Mantenho meus associados atualizados por informativos e publicações colaborativas, que são escritas pelo verdadeiro protagonista desta história, você. Você pode não ter me visto nascer, mas saiba que contribuiu para que eu estivesse aqui hoje. Afinal, sou feito por pessoas. Se já me conhece, é associado ou contribui com a minha causa, o meu mais sincero obrigado. Se não me conhece, tenha certeza, minhas portas estão abertas para novos associados que tenham o desejo de escrever novas páginas desta história. Apesar de ter nascido no passado, sempre atuarei por um bom futuro. Muito prazer, somos o Instituto de Engenharia.